those who've joined us in the theatre here in the Birmingham Museums, but also to those online, of whom I hope there are quite a few to make up for our numbers here. But everybody's very welcome to these meetings. Those here physically here, if you wouldn't mind signing the attendance sheet, it gives me a figure I can hand back to the museums department, and all those online pick that up from technicians. So I think in terms of general operation, I'll hand over to Philip for the housekeeping bit.
Yes, just usual sort of safety announcements and things. We're not expecting any kind of emergency, but if something were to happen, we will initially be advised of a potential problem by a female voice over the tannoy, and if it turns out to be something serious and we actually have to evacuate, a male voice will take over and tell us what to do, which will basically go out the way we came in. But should that be inaccessible for whatever reason, I think there's another way out of the top left corner of the room. There are fire extinguishers around and about. If you need a loo, there are ladies and gents in the foyer, and if you need to leave during the meeting, the doors will release out to the main building if you press the illuminating button. So thank you very much.
Yes, I'm waiting for the next emergency announcement because I actually rashly had a read of the instructions for staff as I was coming in on Monday. And it may well be now that there's a male voice does the initial introduction and a female voice tells you to get out of the building. But I'm still waiting to discover what they've done with that. So, moving to our speaker. Now, John has spoken to us in the past and has explained about his background initially in engineering and then moving across to medicine and finishing up as an anaesthetist in hospitals. But he only just recently pointed out to me that great long string of initials, very impressive on the board, several of those aren't even anything to do with his two careers. There are other interests he's taken up. So we're looking forward to hearing a bit more from the medical side. We've heard quite a lot from the technical side that you've covered in the past, John. So I think we'll hand over to you and see how it goes. Sorry? No, I can't hear that.
Okay. Well, I'm going to start with a slide that I've shown before in other lectures where I was just pointing out what I used to do for a living. As we said, I was an engineer first. Then I went into, I couldn't stand the sight of blood when I left school. But I ended up, after an apprenticeship in electronics with Mullard Radio Valve Company, as part of Philips, so I ended up dealing with X-ray tubes and then moved across to the only job which was available when I finished the apprenticeship, which was the medical division of Philips. And after I realised that blood under control was not quite as bad as I thought it was, and also Philips wanting to put me into a management stream, which I hated the idea of, I bolted and went and read medicine. And postgraduately, I shouldn't have been an anaesthetist really, because I can't do crosswords, but that's life. And this, I didn't order this drawing to be done. I found it, and the artist's wife or widow said I can use it whenever I like, as long as I don't make money out of it. So anyway, I ended up as doing anaesthesia and intensive care, and those are the biggest specialties in the medical profession, where you're trying to poison someone and using things that they breathe, which might not necessarily agree with them staying alive and conscious. So of these, the oxygen one is, of course, the most important. To put it into perspective, though, general anaesthesia, which also includes when patients are on ventilators in intensive care units, you have to control what they're getting to breathe or what's being pumped into them very carefully. And of course, the most obvious one is oxygen, and you want to see what the level of carbon dioxide is as well, but that's another lecture altogether. To keep them asleep in those days, nitrous oxide, which is a gas, these are vapours, and these were vapours that we use but aren't anymore. Trichloroethylene is sometimes used by midwives as a vapour because it gives good pain relief. But anyway, the trouble is that this lot are all terrible greenhouse gases. Nitrous oxide is 10 times worse as a greenhouse gas than carbon dioxide. So very recently, it started to happen when I was still doing anaesthetics. We moved over to what's called TIVA, which is total intravenous anaesthesia, where you're not using these agents to actually keep the patient asleep. Obviously, you still want to measure oxygen and carbon dioxide as well, but the other things that we do away with and use things like propofol, which is an anaesthetic agent, and various short-acting opioids, mainly fentanyl, which of course got a very bad press at the moment. But so we're less interested in measuring these, but still very interested in measuring this in what you're pumping into the patient and what's coming out of the patient at the same time. One of the agents that replaces these gases is an intravenous agent, propofol, which we'll might mention at the end, because you can actually measure it coming out in the breath, which gives you an idea of how much, whether you're putting in the right amount. There are umpteen gas laws, I think there are 6 at the last count, which one has to learn about when you're learning to be an anaesthetist and do intensive care. But fortunately, you don't have to remember them all after the exams. The most important one that concerns us is Dalton's law of partial pressures, which basically, as you can see at the bottom here, it's the total amount of gas which you put into the patient. Normally would be nitrogen, oxygen, and the rare gases if they're just breathing air. But you can add these 3 together and call them partial pressures. And obviously we're only going to look at, in this case, oxygen. And now this is just to show you another annoying feature, is that we still, we're half time using SI units, in other words, kilopascals, and half the time we're using millimeters of mercury in pressure in medicine. And I don't think they'll ever change to your blood pressure being measured in kilopascals, as none of us would understand it. But one of the interesting features here is that aircraft cruise at night with a cabin pressure of the equivalent of 10,000 feet. And coming across here, you can see how much, what the actual inspired oxygen is in kilopascals and in millimeters of mercury. And you can see that it's quite a large range. And the reason people go a bit potty in aeroplanes sometimes is not when they're climbing up a mountain at 10 to 10,000 feet, is of course because you get to this pressure of 10,000 feet in an aircraft in a minute or so. And it's that and the alcohol make people go potty in planes. To get closer to the subject in hand, this shows also in the old-fashioned scale and in kilopascals here, what the partial pressure of oxygen is in atmospheric air, and when the thing which you're really interested in what it gets down to at the arterial blood level. Now, it says on the handout that I'm going to talk about these old-fashioned Haldane and whatever. Because of time, I'm going to use the excuse that I'm not going to mention these old-fashioned contraptions because they were only ever used in the laboratories anyway. And also, I don't understand them. I might be a lot of things, but I'm not a chemist. And one doesn't have to be to be a reasonable anaesthetist. What I'm going to mention first is about some disasters that have occurred. Fortunately, as you can see, they were back in the 70s. These were where patients suffered terrible conditions, and some of them died, others were brain damaged, due to the fact that the wrong gases or wrong combination of gases were being applied through anaesthetic machines. And we could talk about that later in the end, but it wasn't the anaesthetist's fault, I hasten to add. It's that the lines, where it was pipe supplied gases, they got misconnected during servicing and things like that by hospital engineers. So the poor old anaesthetist didn't know which of the two gases he was giving, nitrous oxide down the pipeline or oxygen. And soon after this, one of the first interesting things is this chap, Basil Wright, who was very clever and yet didn't like making patents or money or anything. But the thing that he did, which is very simple, was he found that he designed a whistle which you could connect onto an anaesthetic machine before you connected it to the patient. And because of the different speeds of velocity of sound in the individual gases, the pitch of the whistle changed from one to the other. I can't remember which way around it was, but you could safely turn and make sure that you were getting oxygen or nitrous oxide or both. And it was a very simple thing, but and it made life a lot safer. Oh, knew I did that last time I was here as well. That's it. A few words that I might use by mistake because I'm medical and no, I don't think anybody else here is medical. Invasive and non-invasive. Invasive means you're sticking a needle into someone or worse, making big holes in patients. And non-invasive means in this case, you're measuring without doing any damage to the patient. Cyanosis is the technical word if you're going blue because you're not getting enough oxygen. And this horrible word, plethysmography, means it's to do with the changes in volume of something. If you squeeze your finger hard enough, you can actually feel your heart beating because the arterial supply is making your finger swell. And otherwise, and it's called plethysmography. Photoplethysmography we'll come to later, which is where you see it by shining a light through your finger. So having got those bit of terminology out of the way, there are two main groups of times when we need to measure oxygen as gas or in blood. And in gas, you can use paramagnetic, polarographic, galvanic fuel cell, Raman spectroscopy, photoacoustic spectroscopy, and I'll mention all of those. I won't mention thermal conductivity because it's not used anymore, and mass spectroscopy is more a research technique, and you can look it up at any time. But it's certainly not used clinically because the equipment's too expensive. So Michael Faraday first noted that oxygen is paramagnetic, in which it's actually the oxygen molecules are attracted to a magnetic field, whereas all the other gases are repelled slightly. It's very weak, but it's noticeable and fortunately can be used to measure. And the chap who first strung this together to measure gases medically was Linus Pauling, who got a BSc and a PhD. And he's another chap who didn't really want to worry about making money out of anything or patenting anything. And he actually got the Nobel Prize for Chemistry in 1954. And how he demonstrated this was that a strong magnet, which you can see the green bits there, and in the middle was a little dumbbell, and those two blue bits were filled with nitrogen, and it was strung with a torsion wire very lightly. So that if the concentration of oxygen increased in that magnetic field, it pushed the dumbbells out of the way. And he constructed a device to do it, made by a firm called Servomex. And it looked the more expensive one looked like that. You can see initially it had a mirror, like a mirror galvanometer, displaying the here is an analog scale. But later they put a little feedback circuit into it, so it zeroed itself, and therefore they could produce a digital scale. They're beloved of hospital engineers and pipeline people are testing the pipelines, but they're a bit too delicate to let an anaesthetist get hold of. Because we weren't that bad, but we did drop things every now and then. I'll give them a good bashing. So that paramagnetic way of using a paramagnetic system was not yet actually used closely with patients. He actually got the Nobel Peace Prize in 1963. The way that you could use this paramagnetism actually in anaesthetic machines or on monitoring systems in the intensive care unit, using this paramagnetic effect, you had two gases. One here was the reference, which was usually just air, and you hoped it was the normal 21% oxygen. And the sample was being drawn from, a very small sample was being drawn through here by a pump in the machine from the circuit near the pipe that was delivering gases to the patient. And there was an intermittent magnetic field, very rapid here, and this was like a little microphone, a differential pressure transducer here, and it was calibrated. Amplified and calibrated, and so you got a very accurate level of the amount of oxygen that you were drawing into it. Then the story of the fuel cell, which is the rough chronology of it here, just to show where things fit in. There was the invention of Teflon here. By mistake, by a chap called Roy Plunkett. And there were many different effects used for fuel cells to work on in industry. And even the Apollo space missions where they used fuel cells to produce water and oxygen. But in the medical world, it was used, the material was PTFE, and it was, trade name was Teflon. And he did make money out of it, let's face it. And the Teflon membrane, very thin Teflon membrane, was used in two cells, oxygen cells. One was the fuel cell, here, and I'm going to claim immunity from describing the chemistry of that because I write it down and forget it and never remember it again. The only thing I can tell you is that it's used for oxygen gas measurements, and the membrane is tiny bit of Teflon, and it's a voltmeter proportional to the concentration of oxygen. All well and good, but they need to be replaced. The cell needs to be replaced about once a year because, of course, it being a fuel cell, it gets worn out. The other type of cell was called the polarographic version, which is often known by the inventor's name, Clark. Half the time you'll find the word Clark with an E on it, but I'm pretty sure that there's no E, and I've spelled it correctly. But here, this is lasts a lot longer. It's the same membrane that's used, and the voltage here is 0.6 of a volt, and the platinum electrode here with glass insulation. And anyway, the concentration of oxygen this side of the membrane gives you an indication, a linear indication of the current passed through. It will last much longer than a year, as long as you don't poison the membrane. One more interesting thing about it is that it doesn't have to be gas here. It can be a liquid which contains oxygen, and the liquid can be blood, as we'll come to a bit later. The next most common, or thought to be going to be the common machine, because you can measure all sorts of anaesthetic agents with it, is Raman spectroscopy. But it is very expensive, and there are people. It doesn't, therefore, it's used a lot in research or in teaching hospitals for testing things, even clinically. But it's a bit too expensive as a machine to have it as based on an anaesthetic machine. But basically, there's a laser here which bashes the gas which is passed through here from the patient. It's sucked through this little chamber, and it's a helium-neon laser that's used. And the thing about Raman spectroscopy is if you bash a molecule with an intense laser, it will emit, the different gases will emit a secondary radiation at a very small amount, but that amount will be proportional to whatever the agent is you're doing. So the laser here bashes the molecules there. There's a filter which rejects the frequency or wavelength of the laser. And then you have a series of filters, because every gas sends out a different amount of a step away from the frequency of the laser. So it will actually look at oxygen and all of other gases as well. They just have to have the right series of filters in there. But as I said, it's very expensive, and obviously it's not routinely used. This is a photoacoustic monitor, which is in some ways similar to the Raman. This is B&K is Brüel & Kerr, who are very good instrument makers in Denmark. And what you can see here is a wheel here with holes in it. There's an infrared source in here, and this is rotated to switch the source on and off. And it's picked up by the microphone signal the other side of the gas chamber. And electronically, there is a series of filters which will pick out oxygen, anaesthetic agent vapors, all the different ones, each one. It'll also pick up CO2 in the exhaled breath. So this will be during inhaled, and this will be during exhaled. And this would be what nitrous oxide would look like. The thing that I haven't pointed out is that, unfortunately, fortunately for some reasons, you can look at these gases by looking at infrared spectroscopy, which is very easy to do, but oxygen doesn't work in that way. These signals come because if you bash the individual molecules, they will send out a different signal. And so with the mixed gases, the signals will be like that. And this is how they would come out going through the various filters. But they're not coming out as different wavelengths. They're coming out due to a laser or whatever. They're coming up because they're being instantly heated, and as the that disc goes round, instantly heated and not heated, and the signal is picked up by a microphone. Recently, there's been another device which we might talk about at the end, which even picks up very, very low levels of propofol in the intravenous anaesthetic agent, which comes out as a vapor in parts per billion. And yet they're managing to measure it. But that's time at the end or another lecture. So now moving from the gases to looking at blood. Initially, the blood, as far as plasma is concerned, which is the liquid bit rather than the white cells, the red blood cells. So these machines are not connected to the patient. You take a little sample of blood out of the patient in a syringe with heparin in it, so it doesn't clot in the syringe or clot in the machine. And you squirt about, it's a couple of hundred microliters of blood you can do it with nowadays through this valve here. This would be to calibrate it or to flush it between patients. And the tube passes through a device which keeps it at 37 degrees, in other words, the temperature it was in the human body. And it passes through a pH electrode, a reference electrode, PCO2 electrode, and a Clark oxygen electrode. They're all very, very small, so they're not, it'll still work off that amount of blood. And A to D conversion microprocessor will give you those important values there, partial pressure of CO2 and oxygen, and also measure the pH, which is very important. However, we want some other figures out of it, and so there are derived figures. SO2, I'll come to in a moment, is the amount that the haemoglobin molecule is, and cell, how saturated it is with oxygen. But it's derived from here, which means it's not accurately measured. Later machines you have this part in it, the blood gas analysis, and the spectroscopy, which I'll come to in a moment, which therefore gives you an exact amount of, a true amount of the haemoglobin saturation. In this system, this derived bit here, it is calibrated and it's calculated as a series of algorithms, and it's only accurate really for human adult HbA, in other words, normal adult hemoglobin. But if it goes through a separate spectrophotometer bit here, you can get the true value. And then it's sucked out and it's to waste. But this is taking blood samples out of a patient, usually arterial samples. Now, you have to take it from me with some of this, which is quite difficult to explain. But here, this is the amount of the hemoglobin, which is the molecule inside the red cell, how much it is saturated with oxygen, okay? And this is the oxygen partial pressure along here. And as you can see, the tension is both in millimeters of mercury and kilopascals, because we're just annoying, we are. But it means that we're so designed that the hemoglobin is quite well saturated with over quite a good range of partial pressure of oxygen. And if we look at the absorption spectra of hemoglobin as a molecule, it's a bit like this. This is the wavelength of light, infrared here, red here. And when it's got no oxygen on board, the absorption is like that. And when it's fully saturated with oxygen, it's like that. These are known as the isobestic points, where it's exactly the same wavelength, whatever the level of oxygen is. There are some very relevant quotations, which I'll show you the result for in a minute. This quotation here says that few physicians interpret a slight degree of cyanosis. In other words, the patient is white on the blue side of white when you look at them. Most physicians recognize definite cyanosis when it gets as low as 85% saturated, and you can definitely see the patient is blue. Some physicians don't recognize it until it's below that, and consistency is very, very uncommon. Now, the next bit rely on things that have happened, been invented in the past, who've got nothing to do with it. This Isaac Newton statement says, "If I've seen further than others, it is by standing upon the shoulders of giants." And that just about sums it up as far as the measurement of oxygen saturation of hemoglobin. Very abbreviated chronology. Spectroscopy was first started in that era, and as you can see, these people were inventing spectroscopy, and without that none of the things that I'm going to talk about in the moment could be recognised, would have happened at all. Then oximetry, which is where you're trying to find out what the actual level of hemoglobin saturation is, really started in 1864, but the thing that made it whiz on was World War II, where nothing to do with anaesthesia. They were interested in high-flying fighter jets and bombers. And as you can see, there were a lot of people involved in that, right the way up until just after the war. And then we come to we're using all those people's shoulders to stand on. We now talk about photoplethysmography. In other words, plethysmography, like you can feel the swelling of your finger, and photo by light. And the dates for that, I put that one in green because 1937, it was strictly photoplethysmography, which was used on the simple pulse rate monitors, which was shining a light through a finger and watching the pulsation. But then it wasn't until 1972 that, I'm not going to try and pronounce his name, invented the pulse oximeter as we know it today. And Joe Chiani, who's still alive, he's quite young really, did some things that proved it no end, which we'll see in a moment. So going back to the between the two wars, the first of the monitors for the level of oxygen in being carried around by the haemoglobin was invented and was always referred to as Cyclops because it had the two chunks and a power supply, and this bit here, which is enlarged here, which was held on the middle of your forehead by an elastic thing going round. And of course, it was not looking at pulsations at all. It was just looking at very roughly the level of cyanosis. And here you can see it, but you can't see it very well. It's strapped on the patient's head under, these are here under anaesthetic. But this, as you can see, it's quite a contraption just to measure the level of blueness, really, of the skin. Which was, and it was no more accurate really than that, but it certainly was more accurate than people saying whether or not a patient was cyanosed. But they wanted something that could be used in a tank to reduce the level of oxygen, to see what happened to pilots at various levels of altitude. And so Squires, instead of this one here, which went on his head, which was reflective, he made one which was transmissive. It went through the web space here, kept on with a spring. And as you can see, the kit was much smaller. But again, it was still only measuring the level of cyanosis, the blueness, or whiteness. Then there was Glenn Millikan, who made a one which would go on the ear, which again still only measured the level of blueness. That was in 1940, and this is, you know, as far as you could get really in those days of just looking at the skin level of blueness. And in 1970, Hewlett-Packard made a big contraption that went on the ear, as you can see that, and it used umpteen wavelengths, or a lot of wavelengths. It used 8 different wavelengths, and there was a lamp and a filter wheel here with different colour between 650 and 1050 wavelengths. About 20 samples a second, and it could measure saturation, but again, still not looking at actual arterial saturation. And it weighed a ton, 17 kilograms, and it was 13,000 pounds. And of course, this was before the days of light-emitting diodes. One of the things that you're always told when you're measuring things is that you should compare like with like. And unfortunately, the blood gas analyzers, which had spectrophotometers in them, were called coaximeters, and they were working over that coloured visible range. They were used to calibrate pulse oximeters, which were the next thing along between red and infrared. The initial pulse oximeter was made, it was an analog device, and fortunately with an analog device you could actually make a sensor which could look at, because of its filter, could look at an isobestic point, which it did. The device they used was a halogen lamp here with a filter reducing some of the wavelengths, and glass fibre here. And so the signal came through here and went this way and that way. The unfortunate thing about it was that it was very difficult to make the glass fibre things in 1970. A bit later, 1972-ish. And not only that, because it was a halogen lamp, it used to burn the finger, which wasn't very good for you. But it did to a certain extent, because it was looking at two different wavelengths, which were then converted to a ratio between the two, A to D converter and a digital display, a galvanometer and alarms. And it would actually, for reasons we'll see, actually measure the level of haemoglobin saturation in the arteries and not just through the skin and the finger. But it tended to burn the finger, which was a great shame. And then along came this gentleman who, in 1974, used light-emitting diodes. But there wasn't a light-emitting diode at that time which was available at the isobestic point. There was one available at 660, which is red, and 940 nanometers, which is in the near infrared. And it relied on the fact that the Lambert-Beer law, which you can probably see from here, relates the actual absorbance of light to concentration, possibly. The trouble is that the Lambert-Beer law works very well for semi-transparent mediums, and a finger ain't semi-transparent, a fixed path length, which it isn't because it's throbbing, a single unknown, well, there's multiple unknowns, no turbidity and monochromatic wavelengths of light. Unfortunately, this is between looking at clear how it should have been, but its fingers are turbid and they're sort of like that, so you never knew what was coming through, or whether the entirety of the light was coming through or not. But he made it work by looking at 660, which is red, 940, which is in the near infrared. One of the snags is that there were no light-emitting diodes available near the isobestic point. There is now. There's one at 807, a light-emitting diode. But the advantage of the light-emitting diode is it can be switched very rapidly indeed. So what you had was the one finger probe, which you must have all had one applied to at some time, which had a photodetector on one side and two light-emitting diodes on the other side. And they were the power supply switched between these two wavelengths and these two light-emitting diodes at about a kilohertz, between 700 hertz and a kilohertz. Photodetector the other side, amplifier, analog to digital signal converter to a microprocessor, and the microprocessor had alarms, digital display, of saturation of haemoglobin, and it's always, if you these abbreviations this means saturation in percent. P means with a pulse oximeter, arterial with a pulse oximeter of oxygen on the haemoglobin. Whereas if it was done through a blood gas analyzer or a spectrophotometer, that would have a little a, which means it still means it's arterial, but it's not with a pulse oximeter. And digital chart recorder. Obviously a program and some RAM for the thing to work. And the way it worked was the light shining through the finger at those two alternate wavelengths at a kilohertz. This was absorption due to tissue, absorption due to venous blood, which should not be pulsatile, it should be smooth, absorption due to arterial blood, and this is the variable bit of that, which was arterial or arteriolar, which was different from the venous, different from the rest, which is all continuous in time. First thing the device does is these are the two signals, red and infrared, and they're converted. This one here is this one reduced, as you'll see, it's brought down to the same scale. And it's called equalization as it's done. That's with the red to that. So it's the same, but the infrared, they shrunk because they want to make them equivalent, or you need them equivalent. And they're applied, the Lambert-Beer law doesn't work accurately. And that you can only just see that's a curve. So in fact, they take the ratio and apply it to a lookup table in the device. The big limitations of the pulse oximeter, and I'm sure everybody here has had a pulse oximeter applied to them, is it's too damn easy to apply without knowing what the limitations are. And they're very cheap. I mean, you can buy them now for 20 quid. But some of them are good and some of them are bad. The lack of knowledge of the limitations, they're just stuck on by anybody, even the anaesthetist don't know what the limitations are. And I've grouped the limitations into safe and dangerous. And safe, this by the way, is I was going to do this lecture somewhere else 3 years ago, because it's the 53rd anniversary this year of pulse oximeters. But that's beside the point, really. So the limitations I've split up into safe down here and dangerous here. And dangerous, the safe ones are that you can see what's going on. And the only way you can do it really is that whatever pulse oximeter you're using, whether it's a little one on a finger or a rack-mounted one, is you must be able to see the trace, the up and down trace of the pulse oximeter indication of the plethysmograph. If you can't see that, then it's not safe. If you can see that and it's wrong, obviously you know to think either it's a technical problem, mechanical artifacts, EMI, electro-interference, or it's physiological because the thing's pulse dependent. And if you can see that pulsatile trace, then the volume and the rhythm are correct, then you know it's, if they're not there, then you know that you're not getting the right results, and it's quite safe. Dangerous ones are where the thing looks as though it's working, and it's either it's not working and is dangerous. That's a pulse oximeter on my finger, an expensive pulse oximeter. I've got one in the bag. And you can see there's the pulsatile trace. If you can see that, you know that it's safe to take the result. Unfortunately, I seem to be alive at 72 heart rate and 98 oxygen saturation of the arterial blood. In some ways, he made this chap here, Joe Chiani, he's still alive. In 1995, he developed a signal extraction technology called VCT, and it amplifies the signals in such a way that it manages to eliminate all sorts of traces that would otherwise be unsafe. And also, of course, it does display the signal. Now, this it's very complicated, and it's legally very, very tied up with umpteen patients, and goodness knows what. But he saw the sense of making this front end bit and flogging it to everybody else. So it looks like that in the versions that he sells to all the other manufacturers of pulse oximeters. And about 90% of pulse oximeters of any manufacturer have got that in them at the front end. He had the sense to sort that out. And in fact, there's a micro version of it in there. So this costs £250. And that's 10 times what the normal ones sell for. But I wouldn't touch the others with a large pole. So we then come to the dangerous ones. They're where there's a perfectly, they look as though they're working and they're not. And they're the ones you've really got to be switched on about. Accuracy, the cheap ones can be very inaccurate, whereas the expensive ones are within 1% of, in other words, 1% of the read. It's what they're calibrated to be done. They are all calibrated for human adult hemoglobin A, and any other abnormal hemoglobin. If you don't know it's there, you shouldn't trust the pulse oximeter. Some of them have a delay. The delay is when it might be reading a good value, and yet suddenly that value sticks until the pulse oximeter picks it up again. And it might not pick it up because the patient has died or got very low blood pressure. But instead of showing that it's not working, it just delays and holds on to demonstrates the main signal that was there in the first place. They can be affected by flooding, which is light, bright light shining underneath them. Penumbra is when the device is not, the two light-emitting diodes are two different thicknesses because they're not close enough together. The flooding one is interesting in that it can be flooded by too much light, or even worse, Draeger make an operating lamp, small operating lamp, which is used an awful lot, which is LED. And the way, if you turn the LED down, you realise that it's not just dimming it down like you would with an ordinary incandescent bulb. It's flashing, and you can't see it's flashing, and it will interfere with the signal. So they recommend, especially with neonates, that they put a piece of material over the hand to black it out, blank out these very bright LED lamps. The next most dangerous one is, and the most important one, is abnormal hemoglobins. Now, we've pointed out the red and the infrared of the normal oxyhemoglobin and hemoglobin without enough oxygen. It's the ratio between those two. Unfortunately, carbon monoxide really screws the whole system up. So does methemoglobin, which is quite rare, but carboxyhemoglobin is fairly common. It's caused by, as you know, it's caused by carbon monoxide, incomplete combustion, hydrocarbons, petrol engine exhaust, tobacco smoking, 40 gas central heating boilers, barbecues and pizza ovens. And for every 1% of carbon monoxide, which grabs onto the hemoglobin molecule better than oxygen anyway, for every 1% of absorption onto the carbon monoxide onto the hemoglobin, if you add that to the actual saturation of oxygen, that's what your reading will come out as, which means that it's bloody dangerous. This shows it up perfectly. This was a chap who'd tried to kill himself with carbon monoxide in a car. This is the percentage. When he was brought in, he was unconscious and had a very high level of carboxyhemoglobin in his bloodstream. And the blood gas analysis showed this amount. He had 30% carboxyhemoglobin, and the other, the actual hemoglobin saturation was way down here. And they gave him lots and lots of oxygen. But as you see, the pulse oximeter is reading 100%. And as they gave him oxygen over this period of time, which is in hours, the carboxyhemoglobin went. It became more oxyhemoglobin, and so actually the pulse oximeter was 100%, actually went to about 98, which just shows how dreadful it is, the carbon monoxide is. I like this quotation. I've heard it come from several other people. A cigarette is a quantity of tobacco rolled up in paper with fire at one end and a fool at the other, which is very accurate. And this shows, this was an American paper, which shows a series of tobacco addicts, how much carboxyhemoglobin, even after for a quick drag, 8.6% is carboxyhemoglobin. So that means that if it's reading 100, the actual oxygen saturation is only 92, which is not so good. So it's very, very important when you put a pulse oximeter onto someone that you know, have they got any carboxyhemoglobin? And of course, even smoking, you can, and even a dog smoking. And the reason this shows another problem, is that they're used, pulse oximeters are used on all sorts of animals other than adults with normal blood. And there's even been plotted the spectrum for various other animals, dogs, cats, rats, and human beings, which show it's not accurate and haven't been calibrated for adult hemoglobin, or for the dog's hemoglobin, or whatever it is. So how do we get round this? Well, Joe Chiani did something else. In 2013, he registered this, which is a pulse oximeter which uses 7 wavelengths, because the construction of LEDs of different wavelengths made it possible by 2013 for it to be done. And because of that, these much more expensive rainbow pulse oximeters can distinguish between the other, and will actually indicate how much HbA there is. That's fetal hemoglobin, carboxyhemoglobin, methemoglobin. And in fact, it will guess what the hemoglobin concentration is. So ideally, all of them should, all pulse oximeters should have 7 wavelengths or more in them. And that covers that problem there. The other problem that can occur is venous pulsation with some types of valve problems, heart valve problems. You can actually get little, this is the seismograph trace here, and this is a venous trace. And as you can see, this, if it's being picked up by a pulse oximeter, it could actually be reading lower than it actually is. So it's safer really than pulse oximeter. Than carbon monoxide, because it actually reads low. So the future, education, education, education. Stop people just buying pulse oximeters. I'll bet if you've had one put on you, they never asked you whether you smoke or not. And of course, you might come out to 98% and you're a heavy smoker, then it actually would be late 80s, not 98%. All use multiple wavelengths, but the way you can get around that is if a patient comes into a hospital, the first time they measure your pulse oximetry, it should be done with a multiple wavelengths one to make sure that there are no odd hemoglobins. Tunable lasers may well come in. Wearable devices, well, you can still get phones with which have pulse oximeters in them, reflective ones, but I wouldn't trust them for accuracy. And the other thing is the virtual ward. People can be at home being monitored by these non-invasive devices safely and be connected by cell phone. And other variables. It will soon be other things can be measured, like blood sugar, which is much more difficult than measuring a pulse. If you're interested, there's some idiot wrote a book about it, and it went to 2 editions, but still people don't read it, so they're still doing stupid things with pulse oximeters. This is a fascinating old book, which is still available secondhand, about the early measurements, especially around wartime. Any questions? Well, thank you. Exactly an hour.
Right, John. Thank you very much. It's obviously something that you've got to know over a period of time.
Yeah.
And well done, sir. You have picked up a lot of this. Are there any questions?
If anybody's at home and has a question, please use the chat function on the Zoom screen to type in a brief question. If we get anything interesting, we'll read it out or put it up on the screen for an answer. We've got one here. I'll try and bring the microphone over to people.
Thank you. This may seem a silly question, but does heat affect it in any way?
Sorry?
Is it affected by heat, all these readings?
No, they're all the blood gas analyzer sets it up at 37 degrees, which is body temperature, for when you put blood through it. And really, if you are putting blood through a blood gas analyzer in somebody who's pyrexial, you should tell the blood gas analyzer machine and it will recalculate it. But it doesn't make much difference using pulse oximetry. If you're cold, you'll get a much weaker signal anyway because all the vessels shut down a bit to try and conserve heat. But the actual blood, it doesn't matter if it's a few degrees difference, it doesn't make any difference to pulse oximetry.
Thank you. Thank you.
I've got one question myself. We in this room, I think, are all sort of white Europeans. If you've got a dark skin, Afro-Caribbean or South Asian or something, does it make any difference?
It does to a certain extent. It will weaken, it won't alter the value, but it will weaken the amount of signal getting through. Now, several people have done papers showing that there is a difference between the white and Negro skin. But when the Massimo, which is the company which Joe Chiani used to run, and he's with his device, it senses that that's one of the things that it puts right from when it's put onto a skin. The thing I thought was a bit sad, though, they actually published a paper about it, but they didn't show how good theirs was in comparison to the cheap ones stuck on our finger.
Thank you.
But so the majority of them are perfect because they've got Joe Chiani's front end.
I don't think we've got any more live questions. Has anything come through on Zoom at all? No questions on Zoom either. You've obviously covered everything.
Always a bit of a problem. You almost feel sometimes in doing lecture, you've actually got to leave a little gap so that somebody can jump in
Yes, yeah.
and ask you about it. Well, John, thank you very much.
Okay.
It certainly certainly brought home to me the complexity of the business. We always assume you see everything happening on the television with folks being treated in hospital and operations and so on, but the stuff that's going on behind the scenes is well worth knowing about, if only to frighten you.
The thing that frightens me most is that you're going to see a general practitioner and you can see the pulse oximeter on their desk, one of the 20 quid ones, and they never say, do you smoke? Or did you have a barbecue last night? Or, it's crazy. But what I should point out really is that the safest thing to do if you're in a hospital is they should use a multi-wavelength one in the accident department or on the first time on the ward, which shows whether or not you're lying about the smoking. And then if that's fine, then you can use and trust the normal 2-wavelength pulse oximeter.
Personally, having never ever had a single puff, I do look back and think, well, maybe it was a good idea that I went down that line, because certainly you do see other folks, and you still see other folks who are smoking just too much. So, well, thank you very much, John. I think everybody has ground to a halt in terms of any concern about questions and so on, but thank you very much indeed. Can we show our appreciation, please?
Thank you. Thank you.
Right. First thing is, thank you for attending. Thank you to Daniel, the technician, who's kept the audiovisual stuff working. We thank Think Tank generally for providing us with these excellent facilities, which we very much appreciate. Next month's lecture on Wednesday the 7th of January, so I had time to recover from Christmas. 12th night will have been and gone. Wednesday the 7th of January, we have Felix Schmidt, the current president of the Newcomen Society. He's coming to give us a presentation which he originally gave in London as his presidential address, and it is entitled A Short Version of the Long History of Automation on the Railways. Professor Schmidt, Emeritus Professor at Birmingham University, an expert on all things railways, and he has spoken to us before about the construction of the original London and Birmingham railway that was illustrated with the lovely pictures by John Cookbourne, but he will tell us about automation on the railways right from the very earliest beginnings, probably even before the Stockton-Darlington Railway that we're currently celebrating 200 years of, right through to the present day, and possibly some estimates of what may happen in the future. So, excellent lecture, well worth coming to hear him. I think he will probably alter it very slightly to suit a West Midlands audience. So even if you've seen it, heard it before, when he gave it before, well worth coming. Do try and turn up in person, and that will be a very interesting lecture.
Right, finally, yes, there are posters for that lecture. If you've got access,
Green light.
sorry, quick switch, swap over. Yes, if you've got access to a notice board, or you know somebody who might be interested, do take a poster for them. We run these things off, and we keep our fingers crossed that it's actually worthwhile doing that. And as I said, there's a donation, it just helps a little bit with some of the running costs of these lectures. And yes, you know, I'm extremely grateful to Dan, the technician, for regularly providing the service. And sometimes I don't see him between lectures, but he's always here. So thank you very much, Dan, and your colleagues. And all the very best for Christmas and the New Year. We have a new year coming up, so it's got to be better than the last one.
Indeed. So have a good time. One interesting bit of news that some of you might be interested in. The Ironbridge Gorge Museum Trust has announced that it's kind of merging with the National Trust to try and solve some economic financial problems. So probably in the spring, the National Trust will be taking over all the facilities, all the buildings, the collections and so on at Ironbridge Gorge Museums, which should help to solve its financial problems to a certain extent. It also means that anybody who's a member of the National Trust will in due course be able to use their National Trust membership tickets to visit the Ironbridge visitor places. So I thought that might be interesting for people.